Okay, let's talk about AC. Yeah, super cool stuff. It's totally different from DC. Actually, yeah, quite a bit different. And there are a lot of really interesting attributes about DC and benefits to, sorry, AC, benefits to AC. There's cool stuff about DC too, but let's stick to AC. AC is quite fascinating, and it's different than DC. It's got a lot of weird stuff that goes on, and it has some kind of almost magical abilities. So what we're going to do in this particular lecture, we're going to identify sinusoidal waveforms and figure out how to measure the characteristics of them. That makes a lot of sense. And you know what? We're going to talk about how they're generated. So how we actually generate AC. And we're going to talk about the various voltages and current values of a sine wave. Wait, what? Really? There are different values of a sine wave? Yeah, there are different it's not just like current anymore. It's not just voltage anymore. It gets really deep. Okay, and the other thing is we're going to describe angular relationships, sine waves, which is going to help us to kind of move on when we actually start talking about phase shifts and stuff in Mechatronics 1. So we'll just kind of touch on that. We're not going to get too deep into it, but just so we learn some terminology. And we're going to mathematically analyze a sinusoidal waveform. Yeah, and take a look at it. There are lots of different ways to unpack it, and we're going to discover a little bit about why we may unpack all these different types of ways of looking at either voltage or current in a sine wave. And we're also going to see that we can apply these basic rules that we've learned in DC, like, Ohm's law and Kirchhoff's law. It's actually just the same. They're the same rules, absolutely, hands down, with AC. Although with AC, there are kind of different ways to apply them. Yeah, it's pretty neat. And then we're also going to look at waveforms that actually have AC and DC together. Yeah, you can actually add them. It's pretty cool. So what we're going to do is just kind of define AC and DC. So we know about DC, direct current. It goes out of the battery, it goes through the load, and it goes back to the battery again. Well, in AC, we don't actually use a battery. We use a generator, an AC generator. And what's going on here is that the current actually comes out of the generator, it goes this way, and it goes a certain distance, but before it gets all the way back here, it stops. And it just turns around and goes back. So it goes back and forth and back and forth and back and forth and back and forth. So the same electrons are actually going through this load all the time, because they go back and forth and back and forth and back and forth. How often do they go back and forth and back and forth? Oh yeah, that matters. Let's continue on. Yeah, good question. I'll answer that a little bit later. So this is actually how we generate AC. What's going on is that this is so cool, Faraday, which is, I could stop and do a whole lecture on Faraday. Actually, I think I will next week. So when we talk about magnetism, Faraday's a really cool guy. What he did was he took a conductor. Let's just pretend that my pen's a conductor. And he put it through a magnetic field. And he found that when he put it through this way, actually, there's EMF. What's EMF? Oh yeah, electromotive force. Yeah, EMF. So there's actually this force pushing the electrons either that way or that way. And you know what? If we actually have a loop, we have current. That's pretty cool. So, alternating current. Oh yeah, I think we're getting down to like how we generate it. So what happens is there's this conductor and it moves through a magnetic field this way. When that happens, current actually goes this way. Or no, EMF, electromotive force, pushes the electrons this way. Or at least it will push them this way if there's a closed loop. If there's no closed loop, there's still the pressure or the voltage trying to push them. That energy is still trying to push the electrons this way. If I move that same conductor through this magnetic field that's like here, maybe I'll do it kind of like this. There's a magnetic field that's here and here. That's either the north or the south, and this is the north or the south. Now we move this conductor up. Well, what happens is the EMF is actually pushing this way. Yeah, and again, if we've got a closed loop, then there's current going that way too. Well, the whole concept of this going up and down all the time actually creates AC. Why does it go up and down, and why does the potential voltage, or why does the voltage itself, that pressure, why does it vary all the time like a sine wave? Well, because it's actually moving in a circle. Take a look at this. Okay, what's happening is that let's actually start at point B, or maybe just before point B. Okay, so just before point B, by the way, so what's going on is this conductor is rotating like this through a magnetic field. Okay, so just before point B, it's right here, it's actually going this way. So it starts to move perpendicular to the magnetic field. One of Faraday's things was kind of like he discovered that, you know what, if you put this there's a magnetic field here and a magnetic field here, and you put this conductor straight up and down at a right angle to the magnetic field, the actual EMF is at the greatest. But if you go through at an angle, or even if you go through it like this, actually it gets, as I'm doing this, it's greatest, and then it's a little bit less, a little bit less, and a little bit, and if I do this, it's nothing. Yeah. So as our angle of attack changes through the magnetic field, we actually get less EMF. And that's actually why the sine wave happens as this thing's rotating. Let's go through and let's continue watching. Okay, here we go. So right here at point B, what's happening is that this conductor is going through the magnetic field at a right angle. And then if we look at point B here, if we look at this as the voltage signature, right here at point B, it's at its greatest. Yeah, that's because it's at a right angle. So as we continue on to point C, we can see, let's say halfway, we're right here. Well, right here, what's going on is we still have EMF or voltage that's still pushing in the same direction. But because it's at an angle, it actually is less. It's not as efficient. So what's going on is that this actually gets lower and lower and lower until it gets to point C, where it's actually moving perpendicular to the magnetic field lines. And nothing happens. Yeah, we get nothing. We have no voltage. Oh, look at that. There's no voltage. So at point C, the voltage is 0. Okay, well, guess what? This starts going down through the conductor the other way. Remember, when it goes the other way, the EMF is in an opposite direction. Yeah, well, that's why we get kind of voltage pushing the electrons the other way, or alternating the direction of the movement of the electrons. So the voltage actually flips around, the polarity actually flips, and it starts to go down and down and down until it gets to point C. Sorry, let me actually do this. Let me say that again. It kind of goes up and up and up and up and up in a negative direction, right? Because as this is going down, it's getting closer and closer and closer and closer to a right angle, so it's becoming more and more efficient. So the EMF is greater. It just happens to be, pushing in the opposite direction. But it's greater until we get to point B, where it's at the greatest, and then it starts to lower and lower and lower. So at this point, it gets lower and lower, and then we get to point A, it's 0. Because it's moving parallel to the magnetic field. So how this looks more, let's take a look at this again, and we can see some kind of different cycles here. So this is actually taking a look at each one of these cycles depending on kind of in perspective, to the sine wave itself. So what's going on here is that when this thing is at a right angle, it's moving at a right angle to the field lines. What's going on is we've got 0. And here it's moving at perpendicular, so it's greatest. And then here again, it's moving parallel in the opposite direction, but still it's parallel. So we get nothing, and then as we go down, it continues, and it's greater and lower here. So that's just another way of looking at it. This slide and this slide are kind of just the two ways of looking at the same thing. Now, this is going to be touching on, I went back, let me go back a little bit. I said, it changes, right? It changes back and forth and back and forth and back and forth, and but how fast does it do it? Well, let's actually term how fast it does it with maybe another term. So let's slowly walk into looking at the frequency of a waveform, and we'll unpack, there's more than frequency to a waveform, but let's just take a look at this right here. Let's say, okay, so this thing is spinning. Oh yeah, depending on how fast it spins, that would change the frequency. Okay, so this thing is spinning at 60 RPM. So there's this rotation here. It goes from here to there all the way around 60 times. So RPS, pardon me, rotations per second. Okay, good. So it's 60 times. So what's happening is that one cycle takes 1/60th of a second. Yeah, so actually in 1 second there are 60 of them, so vice versa. That's how you look at it. Now look at this. If I were to increase this to 20 rotations per second, my frequency increases. I get 120 hertz. Or essentially what's going on is that in 1 second, I've actually got, or in a 60th of a second, I have 2 full rotations, or 2 of these full waveforms. And yes, they are sinusoidal. Because this is moving in a perfect circle. Okay, good. The other thing is, we can actually do some weird, funky things where maybe we don't, if we want a higher frequency, we can just spin it a lot faster. Or we can add more magnetic fields. Yeah, it's pretty cool. That's actually what they do with these big generators that are generating power for everybody. Are those things rotating 60 times a second? Dude, that's fast. That's a fast RPM. Let's actually calculate that. 60 times a second times, how many seconds in a minute? Oh, 60. Oh, that's right. Okay, so 60 times, oh, that's 3,600 RPM. That's pretty fast for a big, huge motor. Actually, they're not spinning that fast. They're probably only spinning about this fast. That's crazy slow. That's like maybe 1 RPM or 1 RP, a 60th of an RPM. Like really slow. So how does it actually make 60 hertz? Well, you know what's going on? It's this. Take a look at this. We have one magnetic field here and another magnetic field here. So what's happening here is that actually the more magnets you put in there, you increase the frequency of the waveform coming out of the generator without actually increasing the speed. So those big generators that are generating the power for all of the grid are actually moving really slowly, but they have so many of these magnets through them that they can actually make 60 hertz. By the way, they're governed, so they move very, very specifically, exactly at a certain speed. They can't speed up or they can't slow down, or else we'd get some frequency that wasn't 60 hertz. Because 60 hertz is what we run on our grid. Okay, let's continue on here. So let's talk about AC terms. And there's going to be two things here that are kind of, I don't know, they surprised me a little bit. So let's take a look at this. AC voltages. Oh, so we're going to talk about voltages and current. AC voltages, they switch their polarity. They change their polarity. So they go from negative to positive. I guess that wasn't so surprising, but this is the whole current thing. AC currents are currents which are defined by currents that periodically change their direction. Okay. So what's going on is that if current goes this way and then it turns around and it goes this way and back and forth, which means the voltage actually pushing them this way, and then the voltage starts to push them this way and then back and forth and back and forth. And you know what? Because the voltage does this, the current actually does this. It starts slow and then moves fast and slows down and then turns around, starts slow, moves fast and slows down. Yeah, back and forth and back and forth. They actually do that. It's pretty cool. So the current actually is fluctuating all the time and it's changing its direction. So it's really important to know that. Now, I'm going to define AC voltage a little bit later in another slide that actually when we're adding DC, we actually see some kind of interesting terms. But you know what? However you look at it, when we add DC, as long as we don't add so much DC that the AC kind of disappears, then we can still have AC even with DC as long as these two things are happening. As long as we're changing the polarity of the voltage and we're changing the direction of the current. Pretty cool. And we look at an AC waveform like this, and it's a sinusoidal waveform. Okay, good. So let's unpack a little bit about the sinusoidal waveform, and we're going to talk about kind of how we study the voltage in a sinusoidal waveform and the current too. And we'll see that there are kind of all these different ways of looking at it. Yeah, like with DC, there's only one way of looking at voltage. It's either there or it isn't. But here, it's changing all the time. So let's take a look at some of these things. So what we've got is we've got current and voltage. And we've got this point where it's at its maximum. The current is at its maximum. The voltage is at its maximum. And then there's this spot where it's at zero. And then there's at this, oh, it's a negative maximum. We don't call it a minimum, actually. We just call it another maximum. But it's on the other side. So it's negative. Okay, cool. So, and we do understand that time goes this way. Now we can look at this with time or angular dimension, but we're going to stick to time right now. Angular dimension is a little bit different. We'll unpack that a little bit more in Mechatronics 1. Okay, let's continue. So we've got this positive half and this negative half, and we know that the current goes this way or this way. Now, obviously, these slides are from the textbook. So what's going on is that in this positive direction, we see current traveling out of the negative and going to the positive and vice versa. And that's okay. It's electron theory. We can wrap our heads around both of them. In this case, we're just discussing electron theory. If this was down here and that was up there, we'd be talking about conventional theory, and that's fine. So we kind of define this as the positive side, and we define that as the negative side. So it's important that we do that. Although this maximum and this minimum if this maximum and this maximum are still called maximums, but we call one negative and we call one positive. Same here, positive and negative. So just kind of heads up on that. Oh, and by the way, that's the AC symbol for, that's the source for an AC. That's the symbol for an AC source. So you know what a battery looks like? Well, that's the symbol for a DC source, and this is the symbol for an AC source. Okay, so continuing on here, this is where we're going to add some DC to AC. We're going to take AC, and we're going to offset Yeah, that's a term. So we offset. We kind of bring it up. Actually, we can bring it down as well, but we offset it. We set it off from the axis, from the center of the axis. So we're adding some DC offset. And what's going on is that we're picking up this AC waveform. So my question to you is, well, is this still AC? Because it's weird. It's not crossing this line at halfway. Well, again, if we go back to this slide, the definition is if the polarities are changing, the voltage polarities, and if the current is changing its direction, that's AC. So down here, actually, there's this small point right here where the voltage does become negative and the current does go the other way. So yeah, dude, this is AC. Okay, let's take a look at this. So we've added even more DC. We just turned up the DC. We added more and more and more DC, and all of a sudden we have this large DC offset, and we don't have DC anymore. And sorry, we don't have AC anymore. It's gone. Now the signature, the signature of the AC is still there. But it's not actually AC anymore. It's just varying DC. Yeah, pretty cool, eh? So this is something that we can do. Actually, this helps us when we're amplifying AC signals, because you can't actually put AC through an amplifier. Not really. You have to turn it into DC first, then put it through the amplifier, and then take it out and turn it back into AC again. Yeah, pretty cool stuff. Again, you'll learn that in mechatronics. Cool. So that's AC. This is not AC. It's varying DC. And if we add DC to AC, we get this kind of cool waveform, and it's called DC offset. Or sorry, yeah, we take a DC offset. Sorry, another term here. We couple AC together. AC and DC together. We couple them together, and we create a DC offset. We have AC with a DC offset to it because it's been coupled together with DC. So a lot of terms there. Anyway, there you go. So you understand how that works. Let's move on to identifying kind of when I talked earlier about like, well, it happens every so often. What's the speed of it? How often does it happen? Well, there are two terms that we use to define that. One is frequency and the other is period. Let's talk about period right now. I just wanted to find the symbol and the unit. What's going on here is that we have to be really careful. This is why it's absolutely crucial that we're accurate in our documentation, because the symbol for time, yeah, I'm actually stepping out of what I'm talking about right now. The symbol for time is a lowercase t. Do not use an uppercase T in electronics for the symbol for time. It's fine if you're doing physics and you're talking about temperature, but dude, don't use a capital for time. The symbol for time is a lowercase, because the reason is because the capital symbol in electronics is for period. Yeah, it should be a P, but actually that's for power. It's already used. Yeah, so it's a capital T. So what's going on is the period is defined by the amount of time it takes for one full cycle to happen. So if we take a look at this, it's just from here over to here. Now this is kind of a screenshot from an oscilloscope. Right? So an oscilloscope, it scopes oscillus. Yeah, just like a telescope scopes like tele, which means far away in Greek. Maybe Latin, but I think it's Greek. So what's going on is that an oscilloscope scopes oscillus, or actually it scopes oscillations. Yeah, pretty cool word. So this is like a little oscilloscope, right? So it's a scope that's scoping oscillations in electrical circuits. And what's going on here is that it's seeing the voltage and seeing the voltage go up and then down. So it's identifying an AC waveform, and it's saying, wait a second, let's just pick out one full waveform of that AC waveform and study it. How long is it in between? Like if I had my scale of time, what's that distance on that scale of time? Well, that's called the period, and it's measured in seconds. Okay, so it's important that we measure it in seconds. We could measure it in milliseconds, microseconds, picoseconds, kiloseconds, whatever it is, it's in seconds. And if it's large or small, that's fine. We're going to put a metric prefix on it, but we don't measure it in hours. Okay, so let's continue here, and we'll talk about frequency. And we'll talk a little bit more, we'll unpack frequency a little bit more just by looking at the definition of more of one of these divisions, or one full cycle. And one full cycle is in between any two spots. So I can actually take a full cycle and say in between peak to peak, or in between 0 and 0, or a negative peak and a negative peak. So essentially we're looking at wherever the waveform looks the same again, That's going to be 1 period. And then we define that with a capital T. Now, in this case, we're looking at here, what's the period of this? Well, I've got time on this scale here, and I know, oh, that's in microseconds. Okay, so each one of these is a microsecond. So I'm going to go from, there's 10, 20, 30, 40. Okay, 40 microseconds. So the period of this waveform is 40 microseconds. That's how long it takes just for one cycle. Now, my question is, what's the frequency? How do you figure it out? Well, let's just take a look at it. Before we do the math with the frequency, let's define what frequency is. Frequency is like how often something happens. I mean, when you boil it down really simply, like, okay, so wait a second here. This is for how... What's the frequency of me hitting this with this pen? I don't know, once a second or something. So 1 time per second, maybe? I was probably a little quicker than a second. So maybe in 5 seconds, I might do 8 of these, maybe? I'm not sure. But we understand that it's a certain amount of, it's how many of that happens per unit time. Well, it's actually per unit time is a second. And how many cycles happen in a second? So when we unpack what's going on here in AC, we look at actually how many of those full cycles, how many of those little periods happen every second. And that's our frequency. Now in this case, let's just kind of more look at the kind of just unpack frequency without kind of trying to define what the numbers are. Let's just take a look at this. I've got 1 full cycle here, another full cycle here, and another full cycle here, and another. So I got 4 full cycles, and they happen in a certain amount of time. And that's 1 second, and we call that 4 hertz. But what happens actually if we extend it a little longer and we make the period a lot longer? Well, actually, then our frequency goes down because only 1 cycle happens per second. In this case, 4 cycles happen per second. And in this case, only 1 cycle happen per second. So the frequency is lower because less of them are happening per second. Yeah. So frequency goes up the number of cycles per second. And by the way, frequencies just don't fly around because some people are like, you know, frequencies are coming at us from all directions. No, dude, frequencies don't travel. They're just an attribute of some other thing that is a physical happening. Yeah, like in this case, electrons are flowing back and forth and back and forth and back and forth. What's the frequency of them flowing? Oh, it's an attribute of something actually happening. So anyway, so let's go on and actually take a look at how they're linked. Yeah. How do we actually link frequency and period? Well, this is just, you know, we can see that as the period increases, this is a long period, the frequency decreases. And in this case, as the period decreases, the frequency increases. So it seems as though they're inversely proportional. Well, not only that, but they're actually inversely equal. Yeah, they're equal to each other. I think this is probably the simplest electronic formula that exists on the planet. Yeah, if you can come up with a more simple electronic formula, yeah, I don't know, I'd be pretty impressed. Okay, so what's going on here is that if I know the frequency, I type it in my calculator and I hit the inverse button. Yeah, and then I get the period. Same thing is if I actually have the period and I stick it into my calculator, I just type in the period in my calculator and then I hit inverse, I get the period. Yep. Sorry, I just said that backwards. I get the frequency. If I put in the period, so let's say my period is, let's say 15 microseconds. Okay, 1, 5. I'm actually gonna make sure that I put a bracket because some calculators they inverse the exponent as opposed to just inversing the whole number. So I'm going to do bracket and then I'm going to say 15 E minus 3, did I say microseconds? Yeah, minus 6. And then I'm just going to hit inverse. So that's what it looks like on my calculator. If I hit inverse, I get a frequency of 66.6 thousand hertz. And it's pretty fast. That's really, really fast. Okay, so actually let's do 60th. Now, if I had 60 cycles per second, that's my frequency. Okay, so I'm just gonna type in 60 and I'm gonna hit inverse. That's the period, right? So what's going on is 16.66 milliseconds is how long the period is for a waveform that has a frequency of 60 seconds. So it's that simple. Just kick it in your calculator and hit the inverse key. So yeah, like I said, it's pretty complicated formulation. Yeah, pretty simple. Okay, so yeah, don't forget about the inverse key. Now, it could look like that, or it could be to x to the -1. Mine's x to the -1, but you could have one or the other. But, dude, you know where your inverse key is? I hope you do. Okay, let's continue. So what's going on here is that we're going to unpack different aspects of a waveform. Because, I said, with DC voltage, DC current, it's just voltage, or it's just current. How much is the voltage? How much is the current? But if I were to ask you, hey, what's the voltage of that AC? You'd be like, well, which voltage do you want? Do you want the peak voltage? The voltage where it's at its very maximum. And also, this is the peak voltage well. So this peak voltage and this peak voltage, they're equal to each other. Even though one is negative, what we do is we generally use not just generally all the time, except for some special cases in like physics and stuff, we always use a positive number to represent the peak. Whether it's the lower number or the higher number, it's actually the same value. Because as long as that AC waveform is right along the zero axis, it's going up and down and it's crossing the zero axis evenly, the two peak values are always going to be the same. Okay, so we just take one that's the positive and then there we can put that in. So if you were to say to me, hey, what's the voltage of that? I'd be like, I know what the peak voltage is. And then I could tell you the peak voltage. And you know what? If you knew the peak voltage, you can also calculate the peak to peak voltage. So peak to peak voltage is something that's just a little bit different. Again, it's another way of studying our waveform. And it's actually the value of all the way from the top all the way to the bottom, up and down and up and down. And it's just twice the peak. It's twice the peak. Now, if we put offset in here, just a little bit of offset, peak to peak is not twice peak. But that's if we put DC offset. So you can see that sometimes we may want to actually use one or the other. So sometimes it's actually important that we talk about peak or we talk about peak to peak. So I'm saying that there are all these different ways of talking about the voltage of an AC waveform. And guess what? This is voltage. But I can also say this exact same thing for current. Because if I look at this, that's the peak current, because the current follows the same signature. Its speed increases. It's still going forward when it gets to here. Even when it's going down, it's still going forward. It's just going slower and slower and slower. But that's the signature of how the electrons move, but more specifically, what the value of their flow rate is, or the current. Okay, good. So we can study that in peak to peak, also current or voltage peak or peak to peak. Now, there's this other thing called RMS, which we'll talk about in a second, but I want to just take a look and stop on an oscilloscope. Okay, so we have this oscilloscope here, and we're going to take a look at some of these attributes of an oscilloscope, like the divisions of an oscilloscope, and we're going to figure out what the peak is or what the value is or the actual frequency. So let's take a look at this. So what we've got here on the oscilloscope, remember it's scoping oscillas or oscillations. Okay, good. So we're scoping the oscillations, and each one of these scales represents something. So each one of these divisions has a particular value to it. So from there to there is worth something. Yeah, in time actually. And then from here to there, it's worth something in voltage. So what we can say is, okay, the voltage scale is 40 volts per division. Okay, so in between here and here is 40 volts. In between here and here is 40 volts, and it's consistent. Now, the time scale is 2 milliseconds. Okay, so between here and here is 2 milliseconds. Between here and here is 2 milliseconds. Okay, so it looks like we're studying AC voltage coming out of a socket. Yeah, we are. This is what's going on. You may actually be a little bit surprised when you see what the answer to the peak voltage is. Okay, so if I wanted to figure out the period, I count the number of divisions for one full cycle. And then from there, I just multiply that by the scale. So if we take a look at this, I've got, how many of these divisions are there? Well, it looks like there are about 8.3 divisions. Looks like that. I mean, it's close as I can get. Oscilloscopes will only give you a ballpark. They're not going to give you a really, really accurate reading. They're going to give you a ballpark because it's a matter of how accurate you read the actual scale. Anyway, here we go. So it's 8, ballparking at 8.3. Could be 8.32748. I don't know. It's 8.3. It's close enough. Okay, so there are 8.3 divisions in between here and here. So what's the period? Well, I know each division is worth 2 milliseconds. So if I just multiply them, and you know, you got to put the units in too. Watch this. So I know that the frequency is 1 over the period. Okay, so what's the period? Well, the period is actually how long this takes, and I know it's 8.3 times each one of these. So each one of those is worth, watch this, I could just write milliseconds in there, but I like to write times 10 to the negative 3 just to make sure I get the math right, because I'm going to have to type that in my calculator anyway. Okay, good. So 8.3 divisions. Okay, so that's like a unit. So I want you to put that in times 2 times 10 to the negative 3 seconds per division. And if you do the math, you're just left with seconds. Yeah, I think so. But 1 over seconds is hertz. So in this case, whoa. In this case, we got 60.24 hertz. And you know what? The actual waveform that I'm looking at comes out of a wall. And it's actually exactly 60 hertz. So you can see I didn't get it quite right because I have to ballpark it. And so it's not 8.3 divisions. It's probably 8.31 or 8.308 or some value like that. This maybe it's a little bit bigger. I'm not sure. But essentially, I've ballparked it and it's pretty close. It's 60 hertz. It's good enough for me for now. If I really wanted to, I could use a device to measure the frequency and it would actually give me an actual reading, and that's fine. Most oscilloscopes will actually give you a reading as well, but you have to learn to read them. Okay, good. So now what we're going to do is we're going to read the voltage. Which voltage should we read? The peak to peak or just the peak? Well, actually, if we measured the peak to peak, it might be more accurate because we're using more divisions. We may actually be able to accurately identify how many divisions there are. So I think what I'm going to do is I'm just going to count the number of divisions on just one. So I'm going to go for just the peak. We could calculate the peak or the peak to peak, but here we're going to calculate the peak. Now watch this. I'm looking at this. I'm like 1, 2, 3, probably a little bit under 3 divisions. Under 4 divisions in between here and there. So that maximum voltage is say 3.9 divisions. Well, I know that each division is actually equal to 40 volts per division. So I'm just going to do the math. I'm going to say V peak equals the divisions times the voltage per division. I'm going to put in my value. I'm going to keep on using these units. And I'm going to do divisions and voltage per division. And then bam-o, shmammo, my answer is 156 volts. Whoa, that's a lot. Wait, wait, just hold on a sec. Isn't the voltage coming out of the socket 110 volts? Doesn't like everybody know that? Well, mostly everybody. And isn't like Europe higher? Yeah, Europe's like 220 or something. It's really high. And like, you know, in North America, it's 110 volts. I think mostly everybody kind of knows that. But wait a second, we just calculated at 156. Is something wrong? Well, no. Remember I told you there are all these different ways to look at voltage. Actually more than just one more that I mentioned earlier that's called RMS. So what's going on here is that the RMS value is not the peak value. It's not the peak to peak value. It's actually the effective value. Yeah, now RMS stands for root mean square, okay? And there's actually a formula for that, but we don't need to know it. We just need to understand the concept of RMS. If you want to know the formula, all right, how to actually calculate RMS, it's cool. Go look it up. Okay, so what we're going to do now is we're just going to say, okay, so what is RMS? And I'm going to tell you how to calculate it first, and then I'm going to tell you, like, what it is. And how we've kind of defined what it is without actually doing the math. More practical, hands-on discussion. Okay, so what's going on here is that I'm kind of looking at the kind of the mean, or more specifically the root mean square. So that's my peak value there. And I know my peak value back over here is 156 volts. Okay, so, but if I took 156 volts and I multiplied it by 0.1, pardon me, here we go. If I multiplied it by 0.707, I get the RMS. Now it's actually not exactly 0.707. It's actually 1 over root 2. Yeah. Okay, hold on. I'm going to do that. Watch this. I love the inverse key. I'm just going to hit my square root sign, and I hit the 2, and then I'm going to hit inverse and hit enter. Bam. Okay. So as opposed to me typing 1 divided by and then root 2, I just hit root 2 inverse. The inverse key is very powerful. Cool. So I type that in there and look at that value. Oh, that's 707.707. Often we say 707, but O is a letter. But it's okay. So, because everybody says it. I don't know why. But anyway, so 7.707, 1067812. So 0.707 is pretty close. So we just go with 0.707. So yeah, it's 1 over root 2. That's where the root comes from, the mean square. So yeah, look into that and that's fine. So if I wanted to calculate this value, actually, this is cool. Let me do this. Now remember over here, we had 156 volts. So, and that was kind of weird because you're like, no, it's 110 volts. Guess what? The 110 volts is the RMS value of 156. So watch this. I'm going to type in 156. Now I'm going to just multiply it by 0.707 as opposed to dividing it by root 2. But I can do either and I'll get pretty much the same value. Okay, times 0.707 equals, now I'm going to write it again, 156 divided by the square root of 2, which is a couple extra buttons. And you know what? I'm getting the same value. So, you know, I'm getting 110.12 or 110.3. Dude, it's okay. It's the same thing. So we just roll with 707, and that's fine. Saves you a couple extra steps in your calculator. So the value of a peak voltage with 156 volts is going to have an RMS of 110 volts. Very cool, eh? So now you kind of understand a little bit about what's coming out of that socket on the wall. Or, you know, it's difficult. I have to stop and pause a little bit. I said something that's kind of right, kind of wrong. I said, what's coming out? We're talking about voltage. And then I said, what's coming out of the socket? Well, no, voltage doesn't move. Voltage doesn't come. Voltage doesn't go through. Voltage isn't coming out. Current comes out. Voltage is just pushing. So voltage is the pressure. We know that. It's the push. It's the energy per unit coulomb, actually, per unit charge. It's not about anything that moves. Voltage is not tangible. It's not, you can't hold on to it. But current, well, you can, really. Because, you know, you could fill a capacitor with current or electrons or charge. So current is actually a thing that moves and comes out. So just to kind of clear up my terminology there, we don't say voltage comes out of a socket. Current comes out of a socket, but only if you plug something into it. Yeah, pretty cool. Okay, so let's move on here. And what's going on is that we'll talk about what RMS is a little bit. And I tell you kind of mechanically what it is. And what's actually happening here is it's the DC equivalent. So if I were to say take a light bulb that ran on 110 volts AC, no problem, and I were to plug it in and measure its brightness with some brightness meter, okay, that's fine. So I'm measuring the brightness. Now, if I went over and I found a DC source that was 110 volts and I plugged it into that source, because actually it's just a filament, it would get just as bright. Okay, so it's the equivalent of what DC would be at 110 volts. Remember, my AC is changing. It's going all over the place. So which value do I use? Well, you know what? I'm going to try and find out, hey, if I were to use DC, what value would I need to use to make my thing produce just as much power? So, and then I'm going to say that. So I could just take AC and I could just like, let's just work with 60 hertz. I'm going to take AC and I have this variable voltage thing. So I can vary its maximum and minimum voltage. So I can increase its amplitude. And I'm actually changing, if I have a little dial here and I'm changing the peak voltage. Okay, so I have another power source over somewhere else. There are two beside each other. And one is DC and I crank it up to 100. Okay, so I get 100 volts and I'm running, actually, as opposed to a lighter, or I mean a light, let's talk about maybe a heater. Yeah, or some kind of resistive element that's going to produce heat. Because if I wanted to study power, it's a really good thing to just study pure heat. Because I could then stick it in water and boil some water, and the amount of time it took to boil the water or to change the water 1 degree Celsius or some value, then I can really study the energy and then calculate the power. Okay, good. So I've got one resistive element and I'm running it on DC. And I change my DC voltage so I have a certain amount of voltage. Let's just say it's 100 volts. Okay, so now I got my AC. I'm turning it. And the dial gives me the peak voltage. I'm now running another element, or maybe we'll actually use the exact same element in the same water, and we'll just cool it down. And then we'll plug in the AC source. And I have to turn my dial until my peak voltage is some value that makes the exact same water heat up to the exact same amount with the same rate. In other words, I'm creating the same amount of power. The energy coming out of that heating element is going to be the same rate. It's going to be coming out at the same rate as DC. So it's the DC equivalent. Yeah, and here's a little picture to kind of help you understand that. So what's going on here is that we've got this thing that's radiating heat, and we can study the power here. And if I have an AC waveform, I can adjust it until its value, even though the peak value is 156 volts or less if I'm dealing with 110 volts DC, so that if I can create DC power here and I can do the equivalent AC, then what's going on is that I have this value that's kind of this, maybe a root mean square of my AC that's like an average, but don't ever say that. Did I say that? I did. You didn't hear me say that, did you? Yeah, no, don't call it average. Just don't do it, right? Call it the root mean square. Call it the RMS. So what's the RMS of that voltage? That's a good way to say it. Okay, good. So the RMS is the equivalent to the amount of power that you can generate if you were using DC. So what's that DC value? That's the equivalent RMS value. Okay, good. So the reason I said don't mention average, because there's another way of studying voltage that's actually called average. Let's go back to the other slide. I think I missed something. Yeah, so this is what's going on. This is just another way of looking at this. And take a look at this. So my peak value is 156, and my RMS is kind of somewhere not quite in the middle. It's a little higher than the middle. It's actually about 70% up. Yeah. It's called RMS. Yeah, it's kind of like the average. I said it again. Don't say that. Okay, let's move on and talk about actually the average. So there's actually a slide in here that talks about average, and I'll go back to the other slide. So we have 4 ways of looking at voltage. We got peak, peak to peak, RMS, and average. Now, I'm just kind of letting you know that there's this thing called average, and we will unpack this in mechatronics and understand the value of what's going on here with the average for like what we call well, there's power factor in here and a bunch of other things that we can do, especially when we add capacitors in here, and also when we add when we're rectifying voltage. Average kind of comes into this as well. So it's important to kind of study average, but right now you just have to know that it's 0.637. So there you go. It's just that simple. It's 0.637 of the peak voltage. So whenever we study average, whenever we study RMS, we take the peak and then we do the multiplication from there. Now, let's take a look at some basic formulas. Okay, so if we take a look at these things, we can see that if we want to convert RMS to peak, it's this guy, RMS, sorry, if we want to get RMS from peak, to find the RMS, I take my peak voltage and I multiply it by 0.707. And it's the only time I will ever accept anyone saying, oh, because that was a letter. Okay, let's continue on. If we want to do the same for current, oh, but really? It's the same. Oh yeah, it is the same. So RMS current is the same as well, because remember, the current changes all the time. The current's getting more and less and less and less, and then it stops. And then it turns around and goes the other way. It's changing all the time, just like the voltage is. So we actually have an RMS for current as well. And then we've got our peak here. And this is intuitive, I think, if I wanted to know the peak. Okay, so what's the peak voltage? If I took my RMS and I knew my peak, well, I could just then multiply it by the inverse of 0.707 or by root 2. So when I do this, I actually multiply it by root 2. So I take my value, my RMS, whatever it is, let's say 110, and I multiply it by root 2, and then I get 155. Remember, the other one was 156, and that's actually 155.56, so it's 1.55.6 or whatever, it's 156, whatever, same. So what I'm saying is that to go from one or the other, you multiply by the inverse of RMS, or just RMS, or the 0.707. So it just mathematically, I think it just makes sense. You can just rearrange this and that's fine. Or you could take the peak voltage and divide it by the RMS by 0.707 if you wanted. So I think it just makes sense. You want here's a formula here, here's a formula there. You just flip it around and solve for the other one, and it's just fine. And by the way, you can do the same thing with the current. And over here, peak to RMS. Well, peak to RMS, well, all I have to do is actually multiply it by 2. Yeah, because if I want to know the peak to peak, all I would do is take the peak voltage and multiply it by 2. I think that makes sense. Well, if I only had the RMS, how would I do that? Well, I know how to calculate the peak from RMS, and I could do that by actually dividing it by 0.707 or multiplying it by 1.414 and then multiplying that by 2. Yeah. Or I could actually just take the RMS, divide it by root 2, and then multiply that by 2. So however you want to look at it, it's just a matter of practicing it and just remembering how to do that. Or if you want, you can just go back to the sheet. It's pretty simple. But these are your formulas, quite straight and simple. Okay, good. So we've talked about half cycle. We've talked about all these different ways to study voltage. Let's move on a little bit. And the half cycle. And to calculate the half cycle, this is the formula for the half cycle, and it's that simple. Okay, good. So let's take a look at an example. And actually, this is a practical example. We have this sensor, and this sensor is a vibration sensor. Yeah. And what's going on is that we're tuning a harmonic balancer. Now, there's this machine or this engine or something, and it's got a bit of a wobble to it. And there's something on it called the harmonic balancer. It actually balances out any vibrations that are happening in the machine. But maybe we want to like tune that harmonic balancer a little bit, and I want to know what the frequency of the vibration is so I can properly tune it. So how do I study that? Well, I can actually go get a frequency sensor or a vibration sensor and then see, I said that wrong. I said it's a frequency sensor. There's no such thing as a frequency sensor. It does not exist. There's a sensor that senses vibrations, senses oscillations of some kind of some physical something that's changing, or something we can measure that's changing or alternating, and we can tell you the period of it or the frequency of it. So it's not a frequency meter per se. You're studying the frequency of electrical oscillation if you want to take a look at it, but it's a vibration sensor, not a frequency sensor. Okay, good. So let's move on. Okay, what we've got here is, what is the frequency of the vibration? What is the amplitude of the vibration? Okay, so my sensor is giving me this signal, and I'm looking at it on an oscilloscope. Okay, so what's going on? How do I calculate this? Oh, right, I need my division. So each one of these is actually four divisions. Oh, that's 4 divisions. So sorry, if I go down here, each one of these divisions is 1 millivolt per division. And each one of these divisions, going this way, is 5 milliseconds per division. Okay, good. So I know what each one of these is on my time scale. I know what each one of these is on my voltage scale. And then I can look at this. Okay, so it looks like the peak is 4 divisions. Okay, so it's pretty easy to calculate the peak because I know each division is worth a certain amount. I know how many divisions I have. And then the same thing with the period. So I can calculate the period. I need 1 cycle. How long is it? Well, it's 1, 2, 3 cycles. And I know 1 cycle is 5 milliseconds. So I can go ahead and do the math, right? I can actually do the math here. And I can calculate that the frequency is 6.06 hertz. Okay, so it's going, that's about 6 per second, I think. It's around there, okay? So it's vibrating a little bit. So you know the vibration. It's around 6 hertz. So the amplitude of the actual vibration, it could be just moving this much like this, or it could be moving this. Or could be just doing this, right? So the amplitude is actually seen in the volume, is seen in the voltage, the maximum minimum voltage of the actual sensor that's moving. So the further it moves, the higher voltage gets. So we can extrapolate how far it's moving, or the amplitude of the actual vibration from the amplitude of the volume, or the maximum or the peak of the volume. Okay, let's go back. So I obviously have a problem with volume and voltage. So if you ever hear me say one or the other, just deal with it. Okay, good. So the voltage The peak voltage is going to tell me my amplitude. So I can just do the calculations. The frequency is I know that there's 3.3 divisions, and I know each division is 50 milliseconds. So I'm going to put times 10 to the negative 3 just because I'm going to have to type it in my calculator anyway. And then I can do the calculation at 6.6 hertz. And down here for my amplitude, it's 40 millivolts. So just a small amount. Usually sensors only give you a tiny little voltage. And by the way, they give you very little current, tiny little voltage. But the current's there because there is actually a loop. There's actually a circuit, a full circuit that's going on, but the current's ridiculously small. And the voltage is very small. So sensors aren't very powerful. They're just sensing. Okay, let's continue. So angular measurement. So as far as angular measurement goes, what we want to do is we want to unpack the geometry of the sine wave. So we can actually kind of maybe look back to my generator to see what angle it's at. But that's not the application of that specifically. What we've got is that we've got a rotation. Let me just talk about this. This thing is rotating. It goes 360 degrees every rotation. So what we're doing is we're changing the scale now. We're changing the x-axis scale from time to either radians or degrees, because you know we can use either. So we can use them in radians or degrees. So the angular measurement is kind of where we're at in our cycle. So I could actually say, hey, what's the peak or what's the value of my waveform at like 3.7 microseconds? Well, 3.7 microseconds from where? From the beginning or from when it hit zero? Or, I mean, I could do that if I wanted. And there's actually a way to calculate that. But the other thing is to say, hey, what's the value of my waveform at 62 degrees? That's easy. Or 90 degrees or 127 degrees or whatever my value is going to be. So I can unpack my waveform a little bit more clearly if I have degrees. Because guess what? I'm going to use the function of sine to do that. I think that just makes sense. So angular measurement is something that we kind of need to do to unpack the geometry a little bit. And we can either use degrees, and we know there's 360 degrees in a full cycle. So from here to there is 360 degrees. We know that because essentially for that to happen, my generator has rotated once. Let's just say there are only two magnetic fields on my generator and it's rotated once. So we'll go with that. So when we're studying our waveform, that's 0 degrees, that's 180, and that's 360. So the other thing is that we can use radians as well, and we know there are 2 pi radians in one full cycle. So here's pi. So we're going from 0 to pi radians to 2 pi radians. And you guys know that because 2 pi radians is equal to 360 degrees. Okay, good. So just so you guys have a better understanding, this is just a different way of looking at it or whatever, where my peak amplitude is just 1. So there you go. So these are all the pi's and stuff, and this kind of helps me a little bit because that's a fourth, and that's half, and that's 3/4. So that's 1/4, 2/4, 3/4, and a full pi. If you continue through, you can see a full 2 pi for a full cycle. Okay, so those are radians. And if you actually want to do some conversion, you can do it through this. There's actually a formula. You know the formula for converting radians. I'm sure if you don't, I need you to go and practice that. Also, your calculator is probably going to have a function on it to convert radians over to degrees and or vice versa. So just get to use it because it's important that we understand how to use both. So what I'm going to do is I'm going to talk about instantaneous value. And it's actually really important that we understand that it's just this simple. All it is just very much like the trigonometry you did when you were studying trigonometry and you were looking at the waveform. It's that simple. Don't try and overcomplicate it this. The instantaneous value, either voltage or current. You remember these waveforms can represent current or voltage. So the instantaneous value of a waveform is just pi times theta. Well, times the amplitude. So we take my amplitude and we multiply it by sine times theta. I think I said pi times theta. Pretend I didn't say that. So essentially, I'm going to take my peak value, which is my amplitude, and I'm going to multiply it by sine theta. I think that just makes sense. And again, this just goes back to whatever grade 10 or grade 11 trigonometry whenever you studied that. It's pretty simple. So if I wanted to know the value at any point along here, and if I knew the degree I was looking for, I'm just going to take the amplitude, or the V peak, and I'm going to multiply it by sine theta. Okay, so it's that simple. So in this just example over here, if my peak voltage was 1 volt, let's just say it was 1 volt, and I wanted to know the instantaneous voltage of my waveform at 153 degrees, well, then I just plug the numbers in. It's pretty simple. So my voltage is going to be 0.45Y. But in this because this is a general form right now, well, this is telling me Y. V peak, general waveform. So what I'm trying to say is, what I'm after here is that this can be current, or it can be voltage. So when we study specifically for voltage, as opposed to this general form, which is a Y, what I'm going to do is specifically, I'm going to use a lowercase v. Okay, watch that. It's not an uppercase v. It's not a lowercase v. So the symbol for voltage, by the way, is an uppercase V. It's not a lowercase v. So it's important that you do that in your documentation, because if you write a lowercase v, that's indicating that you're talking about instantaneous voltage. Same thing with current. A lowercase I is for instantaneous current. An uppercase I is for just current. So if I were to study the current here, if I wanted to know my current, I would not put in my RMS current. I put in my peak. Over here, if I wanted to know my instantaneous, I would not put in my RMS voltage. I'd put my peak. So guess what? If I gave you this waveform and I told you the RMS value, you'd have to calculate the peak to put it into your formula. Okay, so it's important that you do that. And the other thing is that right here, we're looking at a lowercase v, and right here, we're looking at a lowercase I. Okay. So there you go. So I'm just saying that, I guess, you know what, I'm choosing 0.707, but that's on 135 degrees. I probably should have used a different value than that, because it's kind of like I'm trying to talk about RMS, but I'm not. I'm just saying, hey, what's the instantaneous value on 135 degrees? So I should have chosen some other value, so you didn't think it somehow is 0.707. The only thing we can learn from this is that if I actually wanted to calculate the RMS for any particular waveform, the instantaneous voltage of a waveform is equal to the RMS at 135 degrees. Just something interesting to note. Okay, so let's move on here. We're going to take a look at phasors. Again, right now, phasors aren't really important. Dude, when we start throwing capacitors and inductors into this equation, into the formula, into the circuit, amazing things happen. Like, I don't even want to get onto that. It's so cool. So in Mechatronics 1, we will unpack that together. Or somebody will. That you might have Peter or something, but it doesn't matter. So you're going to use phasors to analyze instantaneous values of a waveform. So just kind of a heads up. This is what a phasor is. This is what it looks like. Just a term you need to know. You're not going to have to use it for this course other than just knowing they exist. Okay, cool. So the phase of a sine wave. Oh, wait a second. There's phasors and there's phase. Okay, so they're actually different because we're calling them differently. Phasors are just kind of vectors that we use to define a particular value, an instantaneous value at a particular point in the waveform. That's fine. It's just another way of looking at an instantaneous value. In this case, we're looking at phase shift. Yeah, or the phase of a sine wave. Yeah, get this. I could actually take a sine wave, and by the way, we can study this in radians or in degrees. That's fine. I could take a sine wave. Okay, here's my sine wave. I could take it and I could just shift it. I can move it this way or this way. I can do that. We can do that. It's like kind of like magic, right? We actually use capacitors and inductors, and actually devices that have capacitive nature and devices that have a resistive nature, an inductive nature, whatever that means. They actually shift your waveform. And if you have two waveforms and they're shifted, we can study the phase difference between them, or how much phase shift has gone on. Again, it's not phasor. It's how much phase shift has gone on. So a capacitor or inductor can shift an AC waveform in time. They're like little time machines. Yeah, actually they are. They're really cool. But we don't actually make real time machines with them. They're made with something else. Actually, no, I don't think they have real time machines. It'd be really cool if they did. Okay, so let's go on here. Now, when we shift a waveform with either a capacitor or an inductor, what's going on is that we have this terminology that's leading and lagging. So we can say a waveform is leading from where it was before. Or we could say a waveform is leading another waveform. We can also say that one waveform is lagging another one, or another one is lagging another one, or however you look at it. So, I mean, it's all about the perspective from one waveform to another. So if I am, if I'm walking behind you and you're 10 feet in front of me, then you're leading me. Well, you're leading me, okay. So, but I'm lagging you. So however you want to look at it, well, is it lagging or leading? Wrong question. Which one is which? So is Lars leading or lagging you, or are you leading and lagging Lars? The answer to those two questions are going to be different, however you say them. So it's important that we have two waveforms. It's either like the before and after, or actually two waveforms that we're analyzing together. And we can say that waveform A lags waveform B. Or we can say waveform A leads waveform B. It all depends on where they are in time. Yeah, so this is where we go back to our time scale. So we can actually, I know it's in degrees. I know I can see that. I get it. But think of it in time. No kidding. So as long as we're looking at this, we can't, when we study leads and lags, we actually have to say how many degrees they're leading or lagging each other. But whether they're leading or lagging each other is actually dependent on the time. Yeah. So if we take a look at this, is waveform A leading or lagging waveform B? Well, we know they're 45 degrees apart. It kind of says that right here. So if we want to define, is one leading or lagging the other, we have to talk about, if we're going to talk about A relative to B or B relative to A. I think that makes sense. Just getting used to it by practicing this. But essentially what's going on is that in this case, waveform A is said to lead waveform B. Why is it leading? Well, because it's before. Okay, because we're looking at this, at the axis, the x-axis, in time. Just in your head, just think about in time. Okay, so if it's happening in time, is waveform A happening before waveform B? So let's just read the top. It says waveform B is said to lag waveform A by 45 degrees. Why is that? Because it's later in time. Because my scale continues. So I'm going to just move my mouse here. As I go down this way in time, time increases. So this point here is later than this point. So if I look at my peak right here, waveform B peaks right here. Waveform A peaks before waveform B. So therefore, waveform A leads waveform B because it happens before. Yeah, it's pretty cool. So that's a way of looking at it. Although it's kind of weird because I don't know, waveform B seems to be kind of further down the scale. It's in front, so you'd think it's leading, but it's not. It's actually lagging because time, as far as my scale goes, less time goes this way to the left. So it's a matter of practice, just wrapping your head around it. But if you want to wrap your head around it, just say, okay, my scale, my x scale is time. And the smaller the time is over to the left side of the scale. So if my waveform is closer to the left side of the scale, it's leading because it's before in time. Okay, good. So as far as the formulas go, there are two. There's one for leading and one for lagging. So we look at phi and we take a look at this. This is not theta. It's my shift. Over here, phi is 45 degrees. Okay, over here, phi is, in this case, whatever it is. It's not indicated what it is, but it's this value right here. So however much it's leading or lagging, we call that shift the phase shift angle phi. So when we take a look at that, if I wanted to actually know the value here, and you can see that this formula is just a y, because I don't know if I'm studying voltage, and I don't know if I'm studying current. In this case, I'm just looking at a waveform. So this waveform has been shifted, and it's been shifted earlier in time. I've moved it into the negative of my time. So I've moved it less in time. So it's like a little time machine pushed it back in time. So it's actually leading. It's leading by phi. So what's going on here? When it's leading, it's that simple. I just use this formula here and I put a plus. That's it. I mean, it's pretty easy to remember. The only problem is, just going back to this slide, if you ever get mixed up and you say B is leading because it's in front, you're going to put a positive here if you're trying to calculate the phase shift, because it looks like this is phase shift by 45. But you know what? It's phase shift backwards in time, or it's slower. So I'm actually going to use a negative. Ready? Here we go. Bam-o, shmam-o. Look, negative. So when it's moved this way, when it's moved forward in time, it lags. So we use a negative. So we take the peak, we take the peak value, whether it's current or voltage, we multiply that by sine theta minus phi. So it's no longer multiplying it by just by sine of the angle of wherever we want to study it. Remember, we're looking at instantaneous value. So if I wanted to know the instantaneous value right here, I would take my normal waveform. Now we can see, let me just go back here to my regular waveform over here. If I wanted to know the instantaneous value at 90, it's the peak. But if I go down here, this has been shifted. Look at this. Right 90, it's no longer the peak value anymore. So my instantaneous value is actually going to be less. And the way I count, the calculation of it exactly is I find whether it's leading or lagging, and I put a positive or a negative in there. So it's theta plus phi. Theta minus phi. So in this case, all I'm doing is I'm putting a minus in because in this case, it's lagging because it's further in time. Okay, good. So that's what that's all about. And here's some examples here. So if I wanted to take a look at this and I knew my peak value was 20 volts here, and I wanted to know my instantaneous value at any point along this scale here, let's take a look at this. So if I wanted to know the instantaneous value at 180 degrees, right? So if I study that in waveform A, which is not shifted, it's not phase shift, I can actually use the formula and I could add or subtract 0. Wouldn't really matter because it's neither leading or lagging. I mean, really, I'm not going to put that in. I'm just going to use 180 degrees because there's no phase shift for waveform A. So my phase shift is 0, so I'm not even going to actually put it into the formula. So here we go. So I'm going to take my peak value, which is 20 volts, because it says so here, and I'm extrapolating that over here. So it's 20 volts. I'm going to multiply it by sine 180. Now, you could do radians as well. You could multiply it by pi if you wanted, not a problem, but just as long as you're consistent throughout, you're good. So at 180 degrees, my value, the instantaneous value of waveform A is 0. Because the math tells me so. Now, I'm going to do the same thing for waveform B, but I'm going to see I have a different value because it's been shifted. Now, it's lagging. You can see that it's lagging. It's behind, and it's behind by 67.5 degrees. Now, let me just ballpark it, dude. Always ballpark your numbers first. Always say, okay, I'm going to calculate the current. I got 67 amps. I don't know about that because I'm studying the current through a flashlight, so I don't think so. It's got to be 67 milliamps or 6.7 amps or some other value. So in this case, just ballpark it. Now, let me just kind of guess this. I'm looking at waveform B, and I go to 180 degrees, and I go up to here, and I'm thinking, it's probably 18 or 19 or somewhere less than 20 for sure, but it's not 20. So when I do the math, if I get a value that's some value like 150, or even if I get a value of 20 or something, I'd be like, I don't think I did that right. Yeah, always try and extrapolate your values just by kind of what you would imagine. And then from there, if you get some crazy number, just kind of back up and say, I don't think I did that right. Okay, so let's continue on here. I'm just going to guess, and I did. It was like 18 something, whatever. When I did the math, I know that I'm lagging, so I'm going to go in negative because it's forward in time. End up with 18.4. 0.84. Okay, good. And by the way, I'm missing a volt there. Did you catch that? I did. Wow, that's pretty scary. I mean, I'm not going to fix it, but you can take a mark off for my work. Yeah, I should actually give you guys, I should give everybody a mark because I missed a unit. That's ridiculous. I'm speechless. Yeah, that's not right. Okay, let's continue on. Here we go. So this is just an example where we're studying current. And we see that the phase shift is the current has been phase shift as well. Dude, it's amazing. Voltage and current both can shift if we use capacitors and inductors. It's actually quite remarkable how powerful they are and the cool things that they can do. Anyway, here we go. So I've got a phase shift. Now, the phase shift is going into the negative. So it's a positive phase shift. Or it's a leading phase shift. It leads. So I'm going to use positive in my calculation. So over here, I'm going to use a positive because it's leading. I'm going to put the math in here. I want the instantaneous value at this value right here, which looks like 162 degrees. So I want the value, bam, at 162 right there. So I'm going to ballpark it. I'm going to go down here and I'm going to go, okay, so if my maximum here, it looks like 0.8, so that's going to be a 0.8 as well. So I'm thinking, I don't know, 0.72 or something, something like that. Oh, look at that, okay, so it's negative. Now in this case, the current is negative. We were calculating the voltage. It would be negative as well because it would come out as negative, okay? So you can say the instantaneous voltage if this was voltage. Let me go back to my voltage example. If I wanted to study the voltage right here, the instantaneous voltage of waveform A at 270 degrees right here is going to be negative 20. The instantaneous voltage can be negative, no problem. But when we're talking about peak voltage, we just call it positive. So there's a little bit of a difference there. So make sure if you're calculating that, it's negative. And by the way, if you actually put that into your calculator and actually hit enter, you'll get a negative number. So if you put sine this number, it'll just come out negative. You multiply that point by 0.8 and it'll come out with a negative number. So you're going to get negative 647.2 milliamps because it'll be that way in your calculator. Here we go. So yes, instantaneous values can be negative, and your sine wave will just tell you that. Because if you do sine 225, it's negative 1. It's negative 1. If you do sine 45, in this case, if you were to put sine 225 plus 45 into your calculator and put that in your calculator and hit enter, you'd get a negative 1 value, and then you multiply that by 0.8. Anyway, so here we go. So in summary, pretty quick summary, the phase angle is the difference in degrees or radians between a given sine wave and the reference sine wave, so that it's been shifted. And I think that's all I want to say, other than the fact that we've got these terms here. It's 0.707. It's okay. Peak to peak is 2. The average is this value. Keep these numbers in your head, and that's fine. Or you can have that other chart in your head. And when we do write the exam, of course, you'll have those values available. So that's all I have to say about AC. You guys are experts on AC. Go do your homework. And also, right, there is no pre-lecture quizzes anymore, but there are post-lecture quizzes. So do your homework and learn. Okay, bye.